Hello, and welcome to my second video. In this one, I was going to go over a little rocketry simulation I've been working on for the past few months or so. Uh, and we're going to do a general overview of the concepts and mathematics behind the simulation. Slight disclaimer, I will not be able to go into all of the mathematics behind the simulation. That would be a multi-hour video. As you can see, there's a lot of mathematics behind this. Um, Second disclaimer, while at it, I will not be able to release this simulation at the moment. There's a few bugs here and there's a few unfinished features that I want to wrap up, but hopefully I will be able to finish that soon and release it out to you guys. In future, I might do a little series on the simulation actually, so that we can go a bit deeper into the mathematics behind this. So, before we get into the actual explanation, let's just look at what the simulation does. So, we have one rocket, and this rocket has a few different components to it. First, it has this main engine down here. This main engine uses up fuel and oxidizer. It uses the oxygen to combust the fuel, giving us thrust. It also has some RCS thrusters up here. You can see one there, one there, one there, one there. RCS thrusters are a form of monopropellant engine, and they run off of hydrazine, which you can see right there. That's the hydrazine fuel tank. This is the main engine fuel tank, by the way, and this is the oxygen fuel tank. All of these together are averaged along with our rocket's dry center of mass to find our final center of mass, which is right here. Which kind of cool is this is actually dynamic, so if I go into rocket specs and I edit our fuel tank position, you can see it moves our center of mass around, oxidizer tank position. Obviously, if we make this way less, and then I reset the simulation, you can see it will move our center of mass around a little bit there. So yeah, and as we're burning fuel, our center of mass is changing, and we'll get into how that affects the mathematics later, but for now, let's run the simulation. So, I'm just going to start out by burning maybe 10 kilograms of fuel per second, so do something like that. And now we're moving. Now let's get some RCS going. Let's maybe use 5 kilograms of hydrazine per second on this part of the rocket. There you go, you can see that's starting to rotate us. We can actually angle these RCS thrusters as well, so if I do like pi over 4 right there, that's going to angle that, and of course our force then is going to be applied in a different direction, giving a different result. You can also angle this bottom engine, the main engine. Let's do pi, I don't know, completely sideways. Or actually, that's going to be full 180. Maybe I should do pi over 2. There we go. Now we're completely sideways. And that's just going to give us a rotational acceleration there. Yeah, and then maybe we can balance this out a little bit with some thrust from that RCS to put us out of the spin. And you can see all of these different forces are interacting on this rocket to make it move and spin in different directions. And in this video, I want to just give a general overview of how that is computed. As I said earlier, I won't be able to go into all the mathematics. We'll just kind of be gently scraping the surface, but it should give a solid foundation. So I guess a good place to start would be to draw a little diagram of the situation. So let's do that, shall we? Let's draw a little line. That line is going to represent the rocket, partially for simplicity, partially because I'm not fantastic at drawing, I must admit. And there's two things this rocket can do. It can rotate with some angular acceleration that we will call alpha, and it can move with some translational acceleration that we will call a. It also has a center of mass, right? We'll put that in the middle for now. And that's all it can do. So let's look at translational acceleration first. There's a handy little equation for this. that states that force, measured in newtons, equals mass, measured in kilograms, multiplied by our translational acceleration, measured in meters per second squared. Dividing both sides by mass gets us that our translational acceleration equals our force divided by our mass. So let's apply that, shall we? Let's draw another little diagram over here. Let's say we have some force applied down here. We'll call that vector F. Let's assign some values. So let's say we have a mass of 2 kilograms. And let's say our force has a magnitude of 10 newtons. Well then, our translational acceleration A is going to equal that 10 newtons divided by those 2 kilograms, which equals 5 meters per second squared. And it's important to note that this 5 meters per second squared will be in the direction that the force was applied, so it'll be kind of that direction. Now let's look at rotational motion. So there's a couple of things we look at with rotational motion. One of those is torque. There's actually two ways of defining torque. The first one is T for torque equals our moment of inertia, which is kind of like a measurement of how resistant an object is to rotation, multiplied by our angular acceleration, alpha. Another way of defining torque is torque equals R, which is our force's distance from the center of mass, we'll visualize this later, multiplied by F, the magnitude of our force. So because these both equal torque, we can actually set them equal to each other, which is kind of cool. So we can say our moment of inertia multiplied by our angular acceleration equals R, our distance from the center of mass, multiplied by F, the magnitude of our force. Dividing both sides by our moment of inertia gets us that alpha equals RF divided by I. And there you go. Alpha is measured in radians per second, by the way. I should mention that. So let's visualize this and apply it. So let's draw another little diagram here. I might have a slightly off-centered center of mass, so let's put our center of mass up there, shall we? A little off-kilter. That's our center of mass. So we have some force applied maybe right here. We'll call that vector F. So this distance between the center of mass and our force would be R. So in this case, let's set that equal to 2 meters. Let's say we have a moment of inertia, I equal to 5 kilogram meters squared. And let's say that the magnitude of a force is, I don't know, 10 newtons. So we can use that handy little equation that we derived earlier to say that 2 meters multiplied by our 10 newtons divided by our 5 kilogram meters squared equals our angular acceleration. So we can then do some of this computation. So then we get 20 divided by 5 which then equals 4 radians per second squared. And it's important to note as well that we will rotate around our center of mass. So this rotation will look something kind of like this. Now, by now you might be wondering how we actually know whether something is a rotational force or a translational force. So, let's draw some diagrams to help with that. We're drawing a lot of diagrams, aren't we? Going to get very good at drawing lines by the end of this. Huh. Maybe I should have drawn rockets to practice my artistry skills. And we'll have a center of mass maybe right here. We're applying a force that we'll call vector F right there. And let's actually show R as a vector here. So I have R right there. Now, we know we're dealing with rotational motion if vector R dot vector F equals 0, or those two vectors are orthogonal, or perpendicular. Now, to model translational force, let's draw yet another diagram. So we have a little rocket there. We have some force applied here. We have our center of mass up here. And I'll draw R just slightly off to the side, just so we can see what's going on. Call that vector R. Now, we know we're dealing with a translational force if arc cosine of vector R dot vector F divided by the magnitude of R multiplied by the magnitude of F equals 0 radians, or if arc cosine of vector R dot vector F divided by magnitude of vector R multiplied by the magnitude of vector F equals pi radians. Then we are dealing with a translational force. So basically, if vector F and vector R are parallel to each other, or vector F is pointing directly towards the center of mass. And there is a slight exception to those rules that I will go over later, probably towards the end of the video. But for now, let's look at a different example. Let's say we have another rocket, and this time our force is going off to the side here. So something kind of like that. Oh, there we go. So this is still vector F. We still have our center of mass here. And we still have R. Now, what we can actually do is split vector F up into rotational and translational components. So visually, what that kind of looks like is one vector here, we'll call that Fx, and one vector here, we'll call that Fy. So Fx is going to be our rotational component in this case, and Fy is going to be our translational component. So, let's start calculating that, shall we? So we know Fx is going to be rotational, so we then know we can apply this equation that we derived earlier. Right? And oh, that should be the magnitude of R. vector f. However, we haven't actually calculated what fx is yet. So luckily this computation is actually relatively simple. But before we do it, we should label an additional part on this diagram, theta, right there. So, using theta, we can calculate what the magnitude of vector fx is. Specifically, we can write the magnitude fx equals the magnitude of f multiplied by cosine of theta. So, cosine of theta is adjacent, which is fx, divided by hypotenuse, which is f. So if we just multiply it by our hypotenuse, f, we get adjacent, fx. Pretty handy. So substituting this definition into our original equation, we get that angular acceleration equals magnitude r multiplied by magnitude of f cosine of theta divided by our moment of inertia. And there you go. That is the angular acceleration of our rocket. Remember, this is going to rotate around our center of mass and look a little bit like that. Now let's work on the translational component. So we know Fy is going to be our translational component. So we can apply the equation A, our translational acceleration, equals magnitude of Fy divided by our mass. Now we can use a similar process to calculate Fy, where our magnitude of Fy equals magnitude of f multiplied by sine theta this time. So sine is opposite over hypotenuse. Opposite is Fy in this case. Hypotenuse is f. Use a similar process. Multiply both sides by our hypotenuse to attain the adjacent side. And this should also be vector f. Now, again, substituting that equation in, we get that our translational acceleration equals magnitude f multiplied by sine theta divided by our mass. And a good thing to note on both of these is that this is radians per second squared, and this is meters per second squared, like so. Now, if you remember earlier, I mentioned there was a little bit of an outlier to the rule of what is rotational and what is translational force. So let's look at a very specific example here, where we have another rocket. Wow, I'm getting very good at drawing lines. And this time we actually have two forces applied. So we have one force here. We'll call that F1. We have our center of mass. And then we have a second force right here. We'll call this F2. And for now, we're going to assume that this distance is equal to r, which is also equal to this distance, so this is also r. So our forces are evenly distributed around the center of mass. Now, even though this looks like both should be rotational because they're both perpendicular to our r vector, right? However, imagine you have a pencil, and you can actually model this if you have a pencil nearby, and you push on both ends of the pencil at once. It's going to have a translational motion. Even though the force you're applying is perpendicular. So in this case, we can kind of draw a little line across here. So our rotational component, right, this is R, O, T, ooh, lot, for rotational, is going to be equal to this little bit that's left over. So this equals magnitude of F1 minus the magnitude of F2. Now our translational component, we'll call this trans, equals this distance. Well, I shouldn't really say this distance, but a vector with that magnitude in the same direction. So that distance is just the magnitude of F2. So that's just kind of a little outlier case. It is also important to note that if these were not evenly distributed around the center of mass, then our torque would be different on each, and that would add an additional layer of complexity to these computations. It's also important to note that, say we had a rocket, again, and we had our center of mass, and we had one force being applied this way, F1, well, I'll call that F2 for consistency. And we have another force over here that we'll call F1. Then this rule right here does not actually apply because they're still moving in opposite directions. And again, you can kind of model it with your pencil. If you push on both ends in opposite directions, then your pencil will still only rotate. So, now you guys have gotten a little taste of some of the mathematics involved in this simulation. I do hope you enjoyed, and I hope to see you guys next time.